Hello, today we're going to present our bioreactor system that we created as a group. In this project, our main goal was to create, develop, and test a bioreactor system that will be used in a tuberculosis vaccine plant in Uganda. Our bioreactor system is divided into three subsystems for controlling temperature, RPM, and pH in order to help the growth of the yeast that will be used in TB vaccine. The system will monitor and control these values. Next. Firstly, we assigned each group member a different task. During this process, we ensured that each member got a role that they had prior knowledge or experience about. CS students mainly focused on programming the Arduino and designing the GUI, whereas EEE students primarily worked on designing circuits. Even though each member of the group mainly focused on different aspects of this project, everybody was aware of other parts, and all of us tried to find solutions to everyone's problems, irrespective of majors and roles. Next.
In our design, we will take the voltage reading from the thermistor and work out the resistance of the thermistor. During our research, we found that we could calibrate using the Steinhardt-Hart equation, which is shown here. In order to be able to map a voltage reading to a temperature, we had to calculate three coefficients, which are shown here. Once this temperature reading has been calculated and the user has entered the temperature set point, the two values are compared, and we use a bang-bang control system to control this.
For the electronic part, I have used the components from the given template and the component list to construct a heating system which can monitor and adjust the temperature of the vaccine solution. Next. Suppose that the heater element operates at 30 watts. By using the power equation, the current in the circuit could be obtained. Then, I use the Ohm's law equation to calculate the total R. So, a 0.8 ohm resistor is needed to protect the heat element from overload. Also, I have tested all the transistors provided from the list. From my results showing on the table, the MOSFET marked FDP7030 generates the highest power, so I chose it. Next. For the heater, the MOSFET amplifies the current from PWM, and the PWM itself can control the heating power. Otherwise, we could measure the voltage across the heater and calculate the power easily. For the thermistor, the digital output provides a constant voltage, and we use voltage divider to obtain the voltage across the thermistor. Next. By using this equation, the resistance of the thermistor can be calculated. Otherwise, we know that the simulated temperatures are adjusted by the key, so the relationship between the resistance of the thermistor and the temperature can be obtained. The VT graph and the RT graph of this thermistor are shown below. For testing the heat element, I have made a table to show how the power changes when the user adjusts the duty cycle. Clearly, the duty cycle can truly control the power. Next.
Here we can see three graphs. On the left-hand side graph, we can see two lines. The blue one is a graph of the equivalent model on the multisim. The red one is a theoretical graph of the ND06P00103K thermistor, which can easily tell that there's a great difference in resistance around 25 degrees Celsius, which is the expected temperature for the bioreactor to work. The right-hand graph shows the relationship of converted temperature and the actual temperature, and the lower one shows the relationship between them and more clearly around the working range, which we can use for later calibration in coding. Next.
All the results shown before clearly demonstrated that the whole heating system works well as our expectation. For the heat element, the users could adjust the duty cycle to control the temperature rise or temperature drop. For the thermistor, we use the RT graph to obtain the simulated temperature in multisim. Then we use the results from the calibration to convert the simulated temperature into actual temperatures as the real thermistor done. However, for the heating system, there are several limitations. The main problem is that the MOSFET and the thermistor used in the real world were substituted by the equivalent models in multisim, which may lead to the different results in the real project. Next.
In terms of the coding for the heating subsystem, we could have improved in many places. For example, during our calibration process, we only used 3 temperature readings for calculation across a 15 degrees Celsius range. We could have used a larger range in order to ensure that the coefficients that were calculated would be suitable for all the temperatures. In terms of our measurement results, it was generally very accurate. When using the subsystem in SimAVR, the temperature generally stays in the range of plus or minus 0.5 within the set point temperature. However, it does occasionally go past the working range. A solution to this could be using a PID control system, which would be more accurate because it would be a mathematical control system. In terms of system limitations and trade-offs, we've selected Arduino Uno due to its low costs, but it is also quite slow in processing. Next. The stirring subsystem will take a digital input from the light gate, which will be on or off depending on whether light is transmitted or obscured. By taking the time readings and the light gate readings, we will be able to calculate the speed of rotation in RPM. We used an inbuilt function of Arduino coding called interrupts. Interrupts are useful for making things happen automatically. When the interrupt detects that the value of the digital pin has gone from 1 to 0, it will call a function in which the Next.
For the electronic part, two components are given to us, a photo interrupter and a steering motor. The motor is what drives the propeller to steer the vaccine solution, and the photo interrupter is used to provide the RPM feedback to the microcontroller. So this slide is my circuit design on multisim. Here on the left-hand side, we can see the digital output from the Arduino, which is connected to the input of the photo interrupter. And the output of the interrupter is connected to the Arduino input in order to provide feedback. Now let's look at the motor we have in the middle. Since it has a high current load, I am using a MOSFET to amplify the input current. On the left bottom corner is the PWM output. Here should be a slider to adjust the duty cycle. By changing the duty cycle, we are essentially changing the average power delivered to the motor, and hence changing its speed. The diode on the bottom I put there is to protect the electronic components we have here. So this slide is the results I got from the oscilloscopes connected to the motor and the photo interrupter. On the left-hand side is the motor output signal changes with respect to time and with duty cycle adjusted from 100 to 30 to 100%. On the right-hand side is the output voltage of the photo interrupter changing with respect to time. By looking at the results, it is quite clear that both devices are working fine. The voltage increased with time quite rapidly with a 100% duty cycle, and voltage increased with time slowly as duty cycle is reduced to 30%. The photo interrupter output voltage is a square wave and a digital signal, which is exactly what we would expect from such a device in the real world.
In terms of the coding for the stirring subsystem, we could have improved in many places. When using the system on the SimAVR, the RPM generally stays in the range of plus or minus 20 within the set point RPM. However, it does occasionally go past the working range. We could have implemented a PID subsystem like shown here, or we could have changed the condition on the Arduino interrupt from falling to change to make the timing more accurate. Next. For the pH subsystem, the Arduino will read the analog input from the pH pin to the Arduino. During calibration, we found that there was a ratio of 1 pH to a 75 reading on the pin. After calibration had been done, we had to work out a way of coding the peristaltic pumps which controlled the amount of acid. We were told that these had to be controlled using a PCA 9685 chip. By reading the datasheet that was provided, we discovered that we would have to manually turn on the auto increment feature. By using the two values for the pump turning and the two values for when it was not turning and the equation shown, we calculated the PWM cycle. Next.
For the multisim, it has pH probe in the pH pumps. The pH probe is a high impedance device and acts like a sensor. It detects the pH value of the testing solution. In this part, it consists of a 10 million ohms resistor and a voltage source. We can change the voltage source from 0.6 volts to negative 0.6 volts. For the other part, which is the pH pumps, they are high current loads. They are used to change the pH value of the solution by adding base or acid. Both are 6 volts 1 ampere rated pumps. Next. This is my circuit design. For the sensor part, I connected the digital outputs to the pH probe to provide a constant 5-volt voltage. For the other side of the probe, I connected it with the analog inputs, which is an oscilloscope to get the final voltage, and by adjusting the value of the voltage source, I could get a set of values to do the calibration. For the other part, the pumps part, I used two PWM outputs. One is for base pump, the other is for acid pump. For each pump, I use an N-type MOSFET to act like a switch to control the circuit, and a diode to protect the components in the circuit. Next. This is the result of my circuit. The first three graphs show the output voltages of the pumps change with PWM duty cycle. I changed the PWM duty cycle to 10%, 50%, and 90%, and the result is decreasing. For the last graph, it shows the output voltage changes with the voltage source in the probe. Since the Arduino cannot read the negative value, the final voltage should be positive all the time. I changed the voltage source from negative 0.6 volt to 0 volt to positive 0.6 volt. The results are all positive, which means this circuit could solve the problem of negative values. Next.
In terms of coding for the pH subsystem, we could have improved in many places. We were generally happy, but we could have improved. We could have used a mathematical equation for calibration, which would take into account the voltage and the pH voltage and the 10-bit values. In terms of measurement results, it was generally very accurate. However, like with the other subsystems, it would sometimes go out of the working range. So we could have implemented a PID subsystem, a PID control system. And one of the trade-offs was that in Tinkercad, there is no pH sensor, so it was difficult to implement. Next.
From the probe circuit, I recorded the output voltage values from 600 mV to negative 600 mV. By using the equation which is provided by the datasheet, I calculated the pH value when the temperature is 373 Kelvin and make a diagram. The diagram is a straight line. For the simulation, since the multisim could not use two PWM at the same time, I used a potentiometer to simulate the circuit. Although I have already got the values on the oscilloscope, it still will not be the same as our expected, and this is the limitation of my circuit. Next.
Construction of GUI. We chose processing for communicating with the Arduino. We decided to use processing for three main reasons. First of all, processing's control P5 library is very useful for creating graphics. Next, processing and Arduino are very similar to each other in terms of structure. Thirdly, processing syntax is very similar to Java, which we had some prior knowledge about using Java, therefore learning processing was slightly easy. By serial connecting Arduino and processing, we managed to send messages from one platform to the other. At first, we designed the features of our GUI on a paper to ensure that it perfectly fits our problem. Then we placed our sliders, buttons, labels, and graphs on our frame that we created using processing. After ensuring that the design of our GUI is efficient, we connected the Arduino with our processing code. We tested everything to make sure that the connection is successful and all of our GUI features work successfully. In detail, Arduino constantly sends current values for temperature, RPM, and pH to the processing to update the GUI. The processing sends a notification message whenever a button is pressed. Arduino makes required adjustments. Lastly, we use processing to log measured values on a text file. Next. As you can see, our first plan and our current GUI are very similar. Sliders on the left are used by users to enter the desired value. Buttons are used to send those values to the Arduino. Text labels are used to show the current values, and the charts on the bottom are used to show the last 10 recorded values in order to show that each subsystem works fine and the values are stable. Next. As you can see from the screenshot, the bioreactor system also logs each data that it collects on a text file. This allows users to look at the measurements after using the system. Next.
And here is our design for the Tinkercad of each single subsystem, a heating system, the straining system, and the pH system. And finally, here's some conclusion. And overall, the project has been very interesting. We got a general idea about how the job of an electronic engineer and computer scientist are. And there are some possible improvements, like using PID control instead of using band control in order to increase accuracy of the system, and use a little more powerful microprocessor or Arduino in order to speed up the processing time. The GUI could also be a little bit better looking or refined. It could also use slider or RPM meters so that it's easier for the users to use, and improve the coefficients of the Sternhard-Hart equations for the heating subsystem. We learned how to code on Arduinos and how to create a GUI fit for purpose. We also learned about the intricacy of the circuits that go into making such simple system. It has been a very big challenge, but a joy at the same time. Thank you.
I think we did it.